Hello everyone. Let's me start by asking, have you ever gotten into a crowded elevator? Is this safe? Well, today I'm going to show you how digital logic, something we usually find in computers, can actually help protect people in elevator by preventing them from operating when they are overloaded. This project is all about implementing a safety system using basic gates like and or not, etc. To detect when the load is too much. It's smart, efficient, and pretty cool once you see how it works. Like, let's dive in. Introduction to elevator safety system. Elevators are normal part of our life. We use them in malls, office, homes, but we rarely think about how safe they are. Every elevator comes with a set of safety features built in. One of the most important ones is the overload protection system. When an elevator is overloaded, there is a risk of mechanical failure or unexpected behavior. So, having a system that can detect the extra weight and stop the elevator from working is essential. This is exactly what our project focus on. Using, using simple logic systems to add this layer of protection. Okay, what is overload protection in elevators? Okay, let's break it down. What does overload protection means? When the total weight when the total weight inside the elevator cabin exceeds its capacity, sensor detects it. Then the system stops the elevator from moving. Often the elevator will beep or show a message like overload, please reduce weight. Only after people step out, the elevator becomes active again. This kind of automatic response is vital for preventing and wear tear and ensuring safety for everyone inside. Importance of digital logic in safely mechanism. So why we are using digital logic for this? Digital logic system responds initially and don't rely on moving mechanical parts. They can process inputs like signals from sensor and give output in real time. That means less delay and high reliability. Also, logic gates don't wear out like mechanism switches. This makes them ideal for system where safety matters, like in elevator traffic lights or fire alarm. Overview of logic gates. Logic gates are the brain of any digital circuit. They take inputs in the form of binary values, zeros and one, and produce a logic output. There are different types of gates, and, or, not, NAND, NOR, XOR. In our system, we use these gates to make decisions like checking if too many people are inside or not. Understanding Boolean algebra. Okay, to design this logic circuit, we use something called Boolean algebra. It's a way of writing logic expression using symbols. Here you can see and or not. This expression help us describe what we want the circuit to do, and we can simplify to use favor gates to make the system more efficient. Binary inputs from load sensor. Okay, now let's talk about how we get inputs into our circuit. We place load sensor on the elevator floor or near the entrance. When someone steps on them, the sensor sends a signal either 1 or 0. If a person present, the sensor gives 1. If not, it gives 0. These 0 and 1s become the input to our logic gates. With 4 or more sensors, we can detect how many people are inside and whether the total exceeds the limit or not. For overload detection, okay, in this step, we look at all possible input combination from the sensor. For example, if 4 sensor detects weight, each gives 1, like they likely an overload condition. We use the truth table to list these combination and figure out which one should trigger the overload signals. This helps us to detect how connect to the gates correctly. Designing overload detection logic. Okay, now we create the actual logic circuit based on the condition we just identify. Let's say we have four sensors, P1, P2, P3, P4. If all them are in one, it means four people are inside and we might be at or over the weight limit. So we write a Boolean expression like P1 dot, P2 dot, P3 dot, P4. This expression goes into AND gate, and when the all outputs are one and input are one and the output is one, this means overload. Here you can see the circuit. Implementing and or not logic for overload. We can go even deeper by using combination of gates. Together they make the circuit smarter. We create a system where overload turns on a red light, play a buzzer and stop the motor. Elevator enable and disable logic. This is where we make the elevator react to the overload. We use the overload output as an input to a NOT gate. If overload is equals to 1, then enable is equals to 0, means that the elevator motor won't work. Only when overload is equals to 0, the NOT gate gives 1 and the elevator can run and simple but efficient. Hardware and software components. Here you can see hardware component and the software, as you can see. Logic circuit diagram. This is the visual version of our Boolean expression. We draw the gates and connect them, usually wires. It helps us understand the flow of logic, how inputs move through the system, and what output we get. This diagram is also useful during troubleshooting. This you can see the circuit. Simulation using digital tools. Before building the actual circuit, we test everything using simulation tools. Tools like Logicium lets us drag and drop gates and sensors, then test input combinations. It helps us fix error early and improve the design before spending time and money on hardware. Sensor placement and wiring in elevators. Sensor placement is a key. They should be in areas where people actually stand on the floor or near the entrance. We also need the clean writing, no loose connection, so we get the accurate signal. Bad wiring can cause false alarms or system failure. Limitation of basic logic system. Okay, there are some downside to our system. It works with binary output just 0 and 1, so it does not measure exact weight. Also, it may not detect if one person is carrying a heavy load or if the weight is unwellly spread. Advanced features, weight-based system. Okay, to improve, we can add analog sensor with ADCs, analog to digital converters. These read actual weight in numbers, not just 0 and 1. It makes the system more flexible and accurate, but it also adds cost and complexity. Integration with elevator control system. Okay, our system connects to the main control panel of the elevator. It can stop the motor when it's overloaded. It can trigger an alarm. It can work with door sensor and display screens. Everything was in simulation or to make the elevator smarter. Safety and completion standard. Elevator must follow safety rules like ISO or ASME. This ensure every system is tested, inspected, and reliable. Our logic system must also be fail safe, meaning if something goes wrong, it should default to safe state. Future scope, smart and IoT based system. Okay, imagine elevators that connect to the internet. They could send overload warning to building managers or predict heavy uses using AI. IoT and AI can make elevators smarter, managing power, reducing wear, and improving safety. Energy efficiency and cost factor. Okay, logic gate systems are very efficient. They don't use much power and the components are cheap. Also, they need very little maintenance, making them great for basic safety features in budget-friendly buildings. Thank you. And that's a wrap. Thank you for listening me. Presenting by Tanvi Ramani.